I have a theory of spin which finds extra correlation in EPR coincidence experiments, which appears to account for the violation of Bell's inequalities. The question is, how is the correlation from two complementary elements of reality treated in coincidence experiments? I do not think anyone has considered this before. The reason for this communication is to refute the claim by Jan-Åke Larsson, who disagrees with the way I combine the correlations. He states, "Not again, Brian. Correlation from two types of events should not be added. You should use the weighted average. This is Mathematical Statistics 101. I say the two correlations should be added. The two complementary properties I have for spin are its polarization, spin up and down, and coherence, helicity spinning left or right. Now, EAB denotes the EPR correlation. Then I use the sum of the two correlations from polarization and from coherences to give the final correlation. Jan-Åke insists it is a weighted sum given here. There are a number of different correlations to define. EAB is the correlation from my theory. With the subscript W, it is Larsson's weighted sum, and there is the experimental correlation obtained from the experiments. The two complementary attributes are polarization from the Pauli spin vector and coherence from the Pauli bivector. These two give correlation from the polarization, which are denoted by E sub p, and for coherence by E sub c. The correlation from polarization is known to have a maximum CH-SH value of 2, which does not violate Bell's inequalities. The coherence that gives the mustache function and its correlation leads to the apparent violation of Bell's inequalities. The observed correlation is the cosine-like curve, which is the sum of the two. For Larsson's weighted sum, we also need the probabilities for each, and these are denoted by P sub p and P sub c. Larsson's error is that there are no mixed states between complementary attributes. A mixed state, CAB, is an interior point on a convex set, determined by a lever law from the two probabilities giving the relative contribution of the pure states A and B, which are extremal points on the convex set. In contrast, there are no mixed states for complementary attributes. The origin of complementary pairs, polarization and coherence, is the geometric product between the two Pauli spin components. This expression describes the symmetric polarization from the first term and the antisymmetric bivector coherence from the second term. Since I cannot simultaneously be equal and not equal to J, the two terms are complementary. For these reasons, there are no mixed states between complementary attributes. In this case, since we get either polarization or coherence, their probabilities are replaced by Boolean operators, delta P and delta C, which are mutually exclusive. You get one or the other with no mixed states in between. With these, the experimental correlation can be written in terms of the equal and non-equal coincident counts that originate from either polarization or coherence, and weight them not with the probabilities, but with the Boolean delta P and delta C. The correlation can now be written as the sum of two contributions, which is the approach I use, and which agrees with the experimental curves with the minus cosine structure. In my simulation, I calculate the two contributions separately, like here, and then I add them. Experiments cannot presently distinguish between polarization and coherence in EPR experiments. A filter is needed, and it should be possible to build one, and then the clicks can be diverted into separate bins, and the correlation determined as I showed on the last slide. In the absence of such filtering, the EPR correlation is given by the usual expression, which is the difference between the equal and the non-equilibrium clicks divided by their sum. And this gives the experimental minus cosine over filter angle differences of A minus B. Now, correlations are intensive properties. That is, they are independent of the total number of clicks. For example, the following expressions are equal, even though one has 100 times more clicks than the other. Therefore, the correlation is intensive and has the same value for any number of clicks. Now, Larsson's expression is the weighted sum over the probabilities, but the values of the polarization correlation and the coherent correlation do not change as the probabilities vary. This means that the total correlation will differ for different probabilities, which is contrary to the experimental observation. To see this in Larsson's approach, consider experiments with, say, pp equal to 0.4 and the probability for coherence equal to 0.6 to give Larsson's correlation as the weighted sum with these two probabilities. Now repeat the experiment with the probabilities reversed. In both cases, the correlation values for polarization and coherence are the same, but the relative amounts differ. Hence, in Larsson's average, different experiments using different distributions give different correlation, which is contrary to that observed, which is the minus cosine results for all possible distributions. This is a reason to reject Larsson's average. It can be argued that for the coincidence experiments, the probabilities are fixed and cannot be controlled by the experimenter. So we have no choice over the two probabilities, P sub P and P sub C. Nonetheless, any averaging loses correlation. For example, the use of the two probabilities equal to 1/2 give a maximum CHSH value, which will be reduced by half to 1.5 or to root of 2. Whereas experimentally it is 3 from the simulation and 2 root 2 from quantum mechanics. How can including a second source of correlation lead to a decrease in the CHSH value? Clearly, Larsson's approach underestimates the correlation and is therefore wrong. Larsson argues, also incorrectly, that the weighted average ensures that the total correlation is normalized to 1. However, in the theory here, the sum of the two contributions is still bounded between +1 and -1, as evident from the figure that shows the coherence is 0 at the angles of 0, pi, and 2 pi, and so it cannot exceed ± 1. In the EPR case, no normalization is necessary. The quaternion spin or Q spin has symmetry under the quaternion group Q8 rather than SU2. It is one particle in the Dirac field, and not the matter-antimatter pair Dirac proposed. That is, this one particle has two orthogonal axes of polarization which are perpendicular to the linear momentum, just like a photon. The correlation from the polarization gives a maximum CHSH value of 2. This obeys Bell's inequalities. However, polarization is not enough, and the experimental results show that something is missing, which causes the violation of Bell's inequalities. Now, rather than assert that the observed observation of Bell's inequalities is due to non-locality, here we assert it is a result of missing correlation due to coherence. Then the CHSH value increases from 2 to 3, or from 2 to 2 root 2. Note that the correlation from coherence also obeys Bell's inequalities with a CHSH value of 1, and hence the violation is only apparent when the two are combined, whereas separately each obeys his theorem. The simulation gives a CHSH value of 3, which is greater than the quantum correlation of 2 root 2, because the simulation is classical, with the algorithm being deduced from the theory. The polarization correlation involves two spin axes, each contributing a CH value of 1. The bivector is formed from the sum of these two axes, and so there is only one coherent axis, and this contributes a CHSH value of 1 as well. The sum of these three axes implies the correlation gives a CHSH value of 1 per axis. Summing agrees with experiment. Averaging does not. Agreeing with experiment is an important and necessary requirement of any theory. Summing is based upon the complementarity of the attributes. Averaging assumes mixed states can occur. Position and momentum and energy and time exist in different Fourier transform spaces. Spin polarization and helicity also exist in dual spaces. They exist simultaneously, but are not manifest simultaneously. They cannot therefore form mixed states. Correlation is intensive, so changing the distribution of coincidences should not change the total correlation. As intensive quantities, different distributions of coincidences between the two complementary attributes cannot change their value. However, averaging with different probabilities does change the value of the total correlation, and this is wrong. Averaging is deemed necessary to normalize the correlation, but the two complementary attributes added together remain normalized. The conclusion is that Larsson's averaging of two complementary attributes is not well founded and introduces constraints which are inconsistent with the experimental data, leading to spurious, incorrect, and unphysical results if used.